Hello, welcome back. By the way, just so you know, like these YouTube premieres that, again, if you're watching this in real time, at least, they can only be scheduled on like a 15-minute resolution. So even though I'm pre-recording and the video can be whatever length, I still have to kind of watch the clock. And if I'm going to take a break, I don't want to take a 1-minute break or a 16-minute break. So I kind of have to still watch and do 50 minutes or so. And then you get a 10-minute break in between that and this. That's why. That's why I'm still watching the clock. Okay. So again, I was talking about these Lambda functions. Again, I want to emphasize, like, I don't think you ever have to use a Lambda function. Sometimes it'll save a few keystrokes, but otherwise, no. Don't do this. Like, and it's very easy and I understand it, right? You end up with like, oh, I have a key value pair. I just have to extract the first thing out of it. And you end up writing, this code that's like, oh yeah, I'm just going to extract the first thing out of a key value pair. Oh, but it's a string. I really want to, I want the first character of a string. And I want that in lowercase. And you sort of start building this hideous thing. Oh, wait, I actually want to take the first character as a lowercase value, and that I want to pair with 1. Well, what the hell? All of a sudden, you've written this completely incomprehensible line of code that nobody can understand, and you can't understand tomorrow. So why not something like this, right? Give the function a name. Use some decent variable names. What am I even taking? You see, I've already forgotten. Okay, I did have to press a few more keys on the keyboard to get this thing written, but I think we can agree that this is much more beautiful code, and much more readable. And I don't want to debug this if you have a problem with it, and you don't want to debug it if you have a problem with it. Write the more beautiful one. And like I said, Spark tutorials tend to use them because there is nice, it's so easy to give a really quick example using the Lambda expression. Don't learn that lesson. And give the function a name. Think of the name as a free comment. Think of the variable name as a free comment. They're right there. You can explain your code to yourself or to the TA or to your colleagues or whatever. Sorry, 4 spaces, not 3. For me, like if I look at a Lambda function that you wrote for 1 second and I don't understand what it's doing, I would tell you, write it as a named function. Give the function a name, rewrite this code. It's not worth it. It's not worth saving those few keystrokes. Okay, one other note about just sort of Python. Again, this is something that I think a lot of Python programmers also don't get because they've not been forced to. A lot of textbooks are a little bit sloppy, and well, not sloppy. A lot of textbooks don't bother because in a lot of contexts it doesn't matter. But it might for us because we have big numbers and a lot of data. So this seems weird that this doesn't run out of memory, or if I do it, I guess at the Python prompt. Right, I can talk about this thing. That is more memory than my computer has, I think. I can talk about that data collection, but it didn't actually get generated. It's lazily evaluated, and it turns out, like, so if I do this is about to run me out of memory, and I'm not going to press enter there. I've made that mistake before during a lecture. Because if I actually build the list, then it has to be held in memory. So code like this again is, I want to build a collection of all the square numbers from 0 up to n-1. This is one, right? Again, this is the first year programmer code that will do this. This builds a list and appends a bunch of values to it and returns it. That's fine. It's expensive. And if what I'm going to do is something like this, which is like just iterate through each value and like add them up, which is what this code does. In fact, why don't we do that? So again, I called that thing test.py so I can import it. Oh, you know what? I probably can't call it test because test is probably a built-in. Dang it. And it probably imported the module test from somewhere else, and who knows what was in that. So let's try that again. Okay, there we go. Again, maybe I'm glad I did that. Like, I've certainly seen students get into that that problem as well. So again, I can do, well, okay, if I do this, I'm in trouble. I'm about to create this huge list of stuff. And again, maybe what I want to do is not, I don't need to have all of those values in memory in order for that to work. Because it's a lot of values, and I don't need them in memory. I just need to iterate through them. So the more, and again, by the way, this is the same, this list generator, this is exactly the same code. This function does exactly the same thing. It builds the list and returns it. So this list comprehension syntax in Python borrowed a little bit from the functional programming world, but you might have seen something like it in another language. So these two, version 1 and 2, do exactly the same thing. Version 3 does something quite different. It generates the exact same values, but it does it in a way that doesn't actually use a lot of memory. Can I... There's some way to reload a module, and somebody can tell me in the chat, but that doesn't help me because I am recording this in the past. I guess I'm just gonna do that. Yeah. So yeah, both of those generate the list. This one does something different. This one returns a generator object. This code hasn't run yet. I have not yet multiplied 1 times 1 or 2 times 2 or 3 times 3, because what's happening here is, if you've seen the word coroutine, or if coroutine has ever crossed your path, I've effectively created a coroutine here. Squares 3 is still alive. It's running, it's ready to generate those values, but until I start using values out of that generator object, this function is just sitting here on hold, waiting. As soon as I start using them, I think next is the way I want to say that. Yeah. As I start consuming them, this isn't the usual way you do it. Every time I do that, this function wakes up and runs until it yields another value and then goes back to sleep. So this thing is still sitting here. And at some point, I get this like stop iteration flag that happens. It's an exception, I guess, technically. But that's what's happening there. So if what I want to do is add these up, they're equally good, again, or iterate through them. In whatever way I want to iterate through them, it doesn't matter. As if I can basically say for each thing in this result and they work exactly the same way, except 1 and 2 use a lot of memory. 3 doesn't use, well, again, it uses, whatever memory it takes to have that function sort of sitting there on hold. And I can write a version 4 as well. Whoops. I can't believe I spelled 4 wrong. Which is a version analogous to this, except without the square brackets, it's a generator expression, I think. And I don't know how often those things are going to come up for us, but just, so you know. Oh, nope, you need parens around that. Good job, I checked. There we go. So this thing, I can do this. I'm not running out of memory as I do that. If I did that with 1 or 2, I would. Here, I didn't use any. And again, this, okay, I'm about to enter a really, really long loop, but I'm not using much memory to do it. And again, in our world, we might have a lot of data to work with. So yielding, so again, the difference here is either I can build a list and return it, or I can, every time I get a new value in my collection, yield it. So again, it's either return one thing or yield a lot of things. Yielding a lot of things or building a list out of those things and returning the list are kind of conceptually similar, technically different. Again, sometimes we want that. Sometimes it's frankly just convenient. As a Python programmer, if you're doing whatever it is you're doing and you have some big logic and you just sort of you sort of produce output values at a couple spots in your code, you can just yield them wherever you find them. You don't have to build this accumulator list sort of deal. Anyway. One last little note here, as I've been dwelling on the Python basics here for longer than I probably wanted to. Just imperative versus not programming. You have almost certainly spent all of your time as an imperative programmer. All of your programs have been a sequence of steps, right? Do this, then do this, then do this kind of code, unless you've written Lisp, Haskell, Scheme, which is I guess is a Lisp, Erlang maybe, and unless you've done some of those things, F# in the .NET world, you've probably exclusively written imperative code. Again, these things that are explicit lists of instructions. Declarative programming is the style where you express the result you need, but not really how to get it. And I'll argue you've done this in, say, SQL. This doesn't say anything about how to get that value, what order to do the iteration or how to find them, or even if you, if you do something, something like that, what's the algorithm to produce that collection of output? And the answer is you don't know. I have not given you the information to decide because I haven't told you if this field is indexed or not. There's a key on it. So, and maybe this is true of like some tools in imperative languages as well, where you end up writing very declarative things. I haven't really said how to produce that sum. I've just said I kind of need it. You know there's an order of operations there that happens. Except maybe you just declarative in MapReduce. And this is why I'm bringing this up here, because MapReduce, if you just kind of ignore the implementation details, and I've talked about a few of those because sometimes they matter, but if you just say like, oh yeah, what I need is for everything, call this map function, and then everything call this reduce function, and there I'm done, you have kind of ignored the underlying algorithm and just said, here, you've described the result you need, and let the framework take care of the rest. That's a very declarative thing to do, and it's going to happen for us in Spark as well, where almost all the time you ignore that implementation detail of in what order do records get touched, and how do they move from one spot to another. And you almost always can. In the assignments we're giving you in this course, maybe less than usual, because there's a lot of the assignment questions are designed to sort of tease out that difference of when do you have to care about the details of the network traffic or how your data's split or whatever. Most of the time you say, oh, I need this result. Great, thanks. And let Spark or MapReduce worry about the rest. So in some ways, there's this abstraction of we have this data type and we'll take care of everything for you. And you can almost always rely on that abstraction, but all abstractions are leaky. And once in a while, you have to worry about it. So let's actually do some Spark. Let's stop talking about Python in the abstract and actually use a tool. So Spark, again, it's sort of a, I don't know, sibling or competitor maybe to MapReduce. Both of them are, I, the programmer, have to express myself in a way that can be done across a cluster, or in a way that the work can be done out across a cluster. In MapReduce, we get exactly two operations: key value pairs mapped to key value pairs and reduced by key. So for each key, reduce the collection of values. That's fine. Spark likes, MapReduce likes throwing things on disk. The shuffle is actually implemented by effectively writing like HDFS files. So each, as the partitioning happens, each mapper writes one file for each reducer, and then the reducers wake up and start reading those files. So a lot of disk-based stuff. Spark tends to be more memory-based. It's great. Memory's faster than disk. Probably I want that. I guess this isn't really a contrast. We saw that MapReduce can run on your computer or on the cluster. Spark has a few more modes of deployment that are available if you want them or you need them. Spark itself is implemented in Scala, which is a really cool language that I like, that compiles to the Java virtual machine. As a programmer using Spark, you can write Scala or Java or Python or R. In some sense, Scala and Java are a little better. They're a little closer to the original implementation. And in some sense, all four of those are equally good. We'll see in which cases those statements are true. And there's an interactive shell, which is great because you can kind of experiment a little bit more. And I'll show you that in a second here. The abstraction is very different than MapReduce. Again, MapReduce was map and then reduce, and that's all you get. There's a much more expressive API that we get access to in Spark. So, sort of stop thinking very quickly about what I need to do is map, shuffle, reduce, and what I need to do is manipulate my data towards the result I need. That might be map and shuffle and reduce, but who knows? So once again, there's an underlying systems question, right? There's this underlying question of, well, what are the computers doing? What is traveling over the network and when? And for the moment, let's ignore that. It matters, and we're going to have to talk about it because that's how you're going to get the best performance out of these tools in at least the weird cases. For the moment, we're just going to be really declarative and just say, here's a description of the result that I need. Dear Spark, please produce it for me. How it does that, we'll come to later. So this is a perfectly good Spark program that, you know what I'm going to do? Let's see here. I could write it a file or not. I think I'm going to not. I think I'm going to go with the interactive prompt. These aren't in the lecture slides, but this is on the course website. In tech instructions, running Spark, where is it? There it is. So what I'm doing here is effectively running Spark on my computer, which is these instructions, adapted appropriately to this computer that I'm sitting at. It's specified here for the computers in the lab. I think this still works. I'll double check. Hopefully it will by the time you see this lecture. And on the cluster, yeah, some of this setup is done for you. But again, I want to run Spark code either on my computer or out on the compute cluster. The same code should work just like it does for MapReduce. There is, by the way, I've said 2.47 there. There's Spark 3 was released over the summer, 3.01, a little update just around the start of the semester. Officially, we're going to probably keep saying Spark 2.4x here just for this semester because on our cluster, where we can't actually deploy Spark 3 at the moment because, well, if you care, Spark on a Yarn cluster requires this Spark Shuffle service to be running. The Spark Shuffle service is deployed by Cloudera, which is how our cluster is deployed. Cloudera has not yet packaged Spark 3 and the Spark 3 Shuffle service so it can be deployed on a Cloudera cluster. So we're either waiting for the nice Cloudera people or to get bored enough with waiting that we just deploy the stupid thing manually. So on the cluster, it's still a 2.4 Spark. All of the things we can do in Spark 3 as well. In fact, I think I'm working with Spark 3 on this computer. So as you like. one of the things you'll see here in these instructions, there's a couple environment variables that have to get set. Of course, you're going to have to figure out, you know, where your Java 8, Spark does like Java 8. There seems to be a couple incompatibilities with newer versions of the JVM. I don't understand why. And where basically download and unpack the pre-built Spark. And that's really all I've done here. I have OpenJDK installed somewhere. I have downloaded Spark 301, and I'm cheating here. I have done this. So yeah, those two things done just so the commands that I'm about to write and Spark and everything knows how to find its install. And then this is, so instead of running my Python program directly, I'm going to have Spark run it, because of course it has to start up maybe some of my code out there in the compute cluster. So it's kind of a little bit more in charge now. And this is basically, when I say Python, what do I mean? So what I've just expressed is, well, when you try to run Python code for me, use this command to run Python code. Don't use Python 2 or, you know, whatever. And that could be, if you have multiple Python installs or something, you can say like, no, exactly this, run exactly this thing. On the compute cluster, this is all done for us already. There's like whatever environment variables need to be set are set. They're there waiting for us. But, and I guess the other thing there in my cheat sheet is I'm going to add the Spark, the Spark bin directory to my path, just so I can type PySpark and it's there and runs. And that's what I'm going to do. I just started. PySpark is the Spark interactive shell, 301 on a nice modern Python. And it also does some, when you run this interactive shell like this, this gets taken care of. The Spark context that I'm about to, that in my standalone code I've written is generated automatically for me. I guess the other thing I did by way of prep, I did create this directory of many input files. So I don't know. So one of the files looks like this. I just have a bunch of numbers in a text file because it seemed like a perfectly good thing to put in a text file and do a little work with. Just like with MapReduce, my input is split up into many files that are in a directory. I'm going to talk about the directory. So this Spark context object is my entryway into all the Spark functionality. Oh, whoops, in the Python shell, there we go. So that was, again, read all of the things out of that directory as if they're text files. So each line of input becomes a string. This lines object that I got is an RDD. We'll talk about that. But before we talk about that, one of the things I guess I'll give away that you can do on one of these RDD objects is ask, is ask for like the first n things, right? So of course, in general, this might be huge. I don't want to take the possibly trillions of records that I'm talking about here and turn them into a Python list. I want to keep them spread out across my cluster or whatever. But if I want to explore a little bit, I can do that. And in this case, I don't have a cluster. I'm running locally on my machine. This is using all the processor cores. So however many CPU cores I have, I'm using them to do work here. I guess once I start doing work. But that was, are they in that order? No. I wonder what order they were read in, but whatever. Some file here has this as its first line and this is its second line. These are strings because I haven't said anything else. They're just, each line becomes a string. That's the rule of this sc.textfile method. And map is, again, if you've ever used like a map function in any other programming language, it's probably that. It's for each one of these things, call this function with that as an argument and build a collection of all the results. So this, there we go, is that result. So take this, run it through the function int. Int in Python, if you haven't seen it, is a convert something to an integer. So take this string, convert it to an integer. Take this one, convert it to an integer. Take this one, convert it to an integer. and apply that across the however many records are in this underlying data structure. I'm just looking at the first 10 here. Then once I have a collection of numbers, I can start treating them like numbers. So this is like filter is whatever's here. Again, it's for each thing in the collection. So whatever this is had better be a function that takes integers as an argument, because that's what I'm about to give it. And this is probably a good use for a lambda function, right? Like lambda n greater than 0. So if n is greater than 0, return true, right? So this is going to keep all of the records where the thing is greater than 0. So all the positive. So positive numbers is probably a good name for that. Okay, so like that was positive, it got kept. This was negative, it got thrown away. This is positive, it got kept. This is negative, 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 negative. Wow, a lot of negatives. Those all got thrown away. So again, filter is call the function on each element in the collection. Keep the ones where the function returns true. Don't change the values, just throw some away. So that gets me here. So now, again, I look in the documentation and I find that there's a method on whatever this collection is called sample, which is exactly what it sounds like. So this is like keep 1% of the values. But I guess I don't really have to, I guess I'm writing it in 2 lines. So I don't know, I guess I would be slightly surprised if I kept one of those, but you know, whatever, I guess about 1% of those values got kept. And it turns out I can check here. So like all these things are still here, I can count. Ooh, that took some time. Because of course, all these other things, I didn't actually use the entire data set. I didn't have to read all 100 files in order to get the first 10. So Spark didn't. That took a long time because I actually had to read the files there. So I have, what is that, 10 million? 10 million things, so I would expect that to also have 10 million things. That's funny, right? That both of those took a long time? Maybe it's not. This, I mean, I guess I randomly generated the numbers, so this would be about half, I suppose. Yeah. Because again, I just randomly generated numbers positive 1,000 to negative 1,000 or something. So yeah, I keep about half of them there, and then I would expect this to be about 1% of that. And yeah, sure. That's kind of what I was going for. So again, I've written this as if it's a standalone program. So I guess this way, I think everything there should work. So again, like to start that shell, I typed PySpark. If I want to actually run a standalone thing, it's the Spark submit command. So there's a bunch of debugging output there. I will admit that's hard to look at. Oh, geez. But in there was my output, and I'm sure it was the same output. Possibly I got my data in a different order. Anyway, oh no, what was different was this random sampling was different, right? Like this is inherently random samples. So yeah, I would expect different results every time. Yeah. So, okay, there's something called map it's not quite the same as a map reduce kind of map actually, because this is every single thing. Like I get exactly the same number of records in as out, right? So I had 10 million things here, so I got 10 million things here. In map reduce, the map was a one-to-many kind of operation. I had one line of input, I produced 8 words out of it in the word count. So this isn't quite map as map reduce understands it, but yeah, okay, kind of similar. It's a for each apply the function kind of operation. But I got to do these like 3 separate steps or 4 separate steps, depending how you count, all in one program without kind of having to map and reduce and reduce and map and map and reduce. That's pretty compact. And again, I think pretty readable once you get used to the Spark way. So like I said, and you know what, actually one other thing I am going to show since I've got this running, and let's get PySpark back. And I'm going to do, well, I'm just going to copy and paste all that. I'm just going to rerun this whole thing here, just so something has happened. While I have that Spark session alive, I can go to localhost port 4040, and I have this Spark front end that describes kind of what's going on in my Spark universe. So I've done one thing here that actually caused some results, and I don't know how much I can see here. Well, it's a text file, and then some stuff happened. So it was the take operation that actually ran. Again, I can only see so much in here because I haven't done a whole lot of work. But I do get a little insight into what just happened, even the smallest amount. So again, that collection that I kept kind of just referring to as an anonymous collection is an RDD, resilient distributed data set. It's fundamentally it's kind of like a one-dimensional array or something, or a list, except, well, distributed. So when I run this on my computer, okay, like all the data is on my computer, but if I was running this on the cluster, this RDD object is, again, maybe spread across my cluster. I might have 100 worker processes. Each one has 1/100th of my data set. And so when it comes time to do a map operation, they can all operate in parallel. So again, these are partitioned. So I have one RDD that I think of as this huge sort of homogeneous collection that has 100 million records in it or whatever. There's this reality, which is it's partitioned. So I might have get non-partitions. So what I actually have in this particular RDD is, what is it? 10 million records split up into 100 partitions. And well, I guess it's probably because I have 100 files with 10 million lines in them. That's how I got there. Again, each file in my input became one partition in my RDD. So again, this is distributed. I think the word distributed makes enough sense. It's distributed maybe across my cluster, maybe across multiple processes on this computer. It's resilient in the sense that if something fails, Spark does know how to reproduce it. It can sort of start from the input again and reconstruct that slice. But fundamentally, it's, again, a one-dimensional data collection, a list or something. And it holds whatever data I put in it. In fact, we've also seen here, we saw this is a bunch of strings, this is a bunch of integers. Whatever Python values I put in my RDD, it'll happily hold on to them. And I can't change one in place. So I can, of course, take this thing called numbers and I can use it to produce a new RDD. But I can't sort of say numbers, append an element to the end of it or something. Once I create it, it's kind of conceptually unchangeable, even if I might then follow it up with some other calculation. They are ordered, I guess. Like there is a first thing and a second thing and a third thing in that. It's not a set kind of data structure. And again, whatever Python objects I can put in there. So why did this seems like a really funny variable name, but whatever. I guess at some point I must have decided that. So again, numbers, again, I have those 10 things are the first 10 things. Again, I know there's 10 million things in there. Those are the first 10. I can't even. So this is, again, it's a function that takes the one argument. And again, see, I'm using the Lambda function because it just fits on the slide. And I'm doing something really simple as an example. I probably should have named that like create triple or something. But anyway, it's given a number, create n squared, n cubed. So the 867 turns into that. The negative 653 turns into that. 306 turns into that. Again, whatever Python object gets returned here, with the footnote that it has to be picklable. Pickle is the built-in Python tool that turns objects into bytes. I guess like the writable in MapReduce. In MapReduce, we had to implement the writable interface in order to have MapReduce, know how to turn it into bytes and ship it across a network. In Spark, when we're using Python here, it's any object that Pickle knows how to turn into bytes on one side and back into the object on the other. And the tuple here with 3 integers, meets that criteria. Like I said, there's partitioning. So each, again, I think of this as one big data set. It's chopped up into pieces, and each piece can be worked on in parallel. What that means is if I have an RDD with one partition, I'm not really doing anything, I'm not using more than one processor core. That seems a little silly. That probably means this, like, I don't want to say I have 6 processor cores, so therefore I should have 6 partitions. I probably want 60 or something. Hundreds of thousands is a big number, but it's not an impossible number for Spark to deal with. Again, at some point here, there is a little bit of work for Spark to maintain one of these partitions, and again, like, start up, do some work on it, and then move on to the next partition. So millions of partitions is probably bad, but relatively big numbers are fine. Again, in this like, hundreds of thousands. Yeah, hundreds of thousands would be too much. But yeah, hundreds or thousands. Yeah, totally reasonable. Sorry, I misread my own notes there. So I would say 90+% of the time, I think of an RDD like this. I think an RDD is a one-dimensional list-like kind of collection of whatever records I put in it. That other less than 10% of the time, I have to think, oh, no, wait, it's not, is it? It's a bunch of small list-like kind of collections of things that my compute cluster is maintaining with each partition being operated on in parallel. Because I might do something like, well, I mean, I guess even this, right? This is something that can be parallelized, but like even just this. That isn't totally free. So I might do something like, what? I haven't actually, I kind of haven't like gotten to the big conclusion here, which is this. It's all well and good to do some debugging and have a look at the first 10 values, but probably this is going to be the end goal, right? Do a bunch of manipulation and write the output. So that's the thing that actually took some time, because Spark did at this moment have to go through this entire relatively modestly big collection and produce this. And then it produces this directory of stuff. So again, I had 100 input files that turned into 100 partitions in my RDD, which turned into 100, I assume, yeah, output files. They're all about the same size because they were all about the same size when I started. Each one of these has whatever something divided by 100 is. So these are all about the same size. They probably all have about the same number of lines, and they got named part 0000 to n. And I have good confidence that this number is that input number plus 1. So both of those are ways to look at an RDD. And again, they're both correct, depending on the situation, one or the other. Okay, so yeah, I'll take, again, I'm not usually going to use the 50 minutes times 2 in these lectures, but this week I do want to get us into Spark a little bit, so I'm going to use my time this week, a little more than usual. Map and filter are the ones that I just used, and again, both of them take a function as an argument. Map is for each thing in the RDD, call the function, whatever it returns becomes the corresponding element in the new RDD. Filter is a function that had better return true or false. If it returns true, keep it, else throw it away. There's a few things like this that I guess I could, well, I guess I've been calling count, just how many are there, just enumerate them. These return Python values, right? So this is just do all the work, find the largest, or the smallest, or whatever. As opposed to like that map operation, this didn't, you know, I have a Python object that represents the calculation I might do, but the work, if I actually do this work, is going to happen on the cluster or in my worker processes or whatever. And actually, as I look, so now that I've done a little more work, over here in this PySpark, or the Spark, sorry, web interface, there we go. Like I can see like the Spark shell that's open there with its corresponding Spark context has done all of these things, right? So I did a count, I did whatever these things were. In this case, I wrote the file, I'm guessing by Spark Hadoop writer, you know, as the sort of operation name there. I did a max and a min. So yeah, these are the things that happen. And I can see stuff here like, well, it took 2 seconds to work through all of that data and do whatever it was I was doing. And now that I've done some stuff here, I can see here, like, again, I have a 6-core hyper-threaded, so I have 12 threads that can be run, and Spark figured that out, and it's using them all. So, you know, when I do something like that, a whole bunch of additions just happened, and they happened using all my CPU cores. In fact, I think I can hear my fan, like you probably can't hear it in the microphone, but I think I can hear my fan cranking up just a little bit. Like all the CPU cores have turned up at their maximum clock speed and are consuming electricity. That's weird. That's not kind of often the case for most computers. It will be for us. And again, the save as text file I demonstrated there. For each partition, write a file, take the objects in that partition, each one becomes a line in the output. In its sort of default way, it gets converted to a string. So there's a bunch of stuff here. Again, compared to like map and reduce, that was you are going to read input and then map and then shuffle and then reduce and then write output. That's the rules. We have a lot more freedom here, and we can just, whenever we feel like it, do a count, or, oh, count a procs. So again, like if this is a sufficiently large data set, like, you know, maybe counting them all is unreasonably expensive. And okay, this data set's not big enough that I'm really going to worry about it. Oh, you know what? Maybe this is, I just have to let it, I can't quite see what it's doing there. Is it, yeah, I just can't decide if that's part of this weird, I guess I'll do this. Yeah, so it's getting the right, I think this is a, how long should I spend? And yeah, okay, I guess I can't do, I have to give it an integer. I was hoping I could trick it into having to go so fast it had to be actually approximate instead of getting the right number. You know, so how many distinct values are there? Again, that's expensive in general. On a big data set, maybe I'll, so that's probably wrong, right? Like probably the correct number here is 2000, and it's approximate, again, as it did the approx count distinct. Isn't there a true count distinct? Oh, I thought there was. Anyway, again, as I scroll, ooh, there's a join operation. We'll have to come back to that. Oh, there's apparently, you know, I said, oh, these things are partitioned. Apparently we can control that. Oh, there's another one, repartition. That sounds like some other way to change the partitioning of our data collection. And there's a couple other save as if I want, you know, whatever a sequence file is. So I have just a lot more freedom here, it feels like, at least, than I ever did on MapReduce. And I probably want that to happen. And I think that's a good spot to stop. So again, assignment 2 is starting this transition into working with Spark, which I think MapReduce is good for you. Spark is fun. If I had to summarize. So hopefully you agree. Hopefully you enjoy starting to work with Spark a little bit. probably would be my big data tool of choice, maybe with the data frames, as we'll get to as the semester goes on. But otherwise, we'll see you in the lab or on Piazza or wherever we're interacting with each other. Or if not, see you in the lecture next week. Bye.